All right, so let's look at an example. And there's a lot of ways we can approach torque problems, and I'm going to look at this one in a couple different ways. Hopefully this will help sort of build an understanding for how to approach these kinds of problems, because there tend to be a lot of different ways to do them. So let's just take a system like this. What we've got is a bar, and it's attached to a hinge at this point, and it's connected to a wall. And we've got our rod kind of propped up underneath it that's supporting this thing here. So the rod is probably exerting some kind of a frictional force and a normal force on this thing. You can imagine it as being actually attached, so like welded on here or here. But nonetheless, there's definitely a force here. There's some kind of force exerted on the hinge actually helping to hold up the rod. And there's also a force going on here. Let's start off just by looking at the rod. So that rod has a certain mass m, and it's being supported by this bar. So there's actually a force on the rod down from its weight equal to mg, and that force is acting on the rod's center of mass. And now there's another force here. Actually, no, this is the bar. I'm sorry, I misspoke. I said rod. So this is the mass of the bar. The rod is just holding this thing up. So there's also a force from the rod pushing that way. Now, if this thing is at rest, there's actually two conditions that are satisfied. The net torque on it is equal to 0, and the net force on it has to be equal to 0. And we can use both of these. So let's go ahead and start off trying to make use of this fact that the net torque on this rod has to be 0. So I'm going to go ahead and take this point as our axis of rotation, and I'm going to call into the page as positive. Maybe make a note of that over here. In is positive. So what that means here is that mg is exerting a positive torque, right? Use your right hand rule, right? Because it's wanting to make it rotate this way, and my thumb is going down. This force, on the other hand, is pushing up, trying to make it rotate that way. So this force is actually exerting a negative torque. And if this thing is at rest, those two torques are going to have to balance out with each other so that the net torque on the system will be 0. I'm going to go ahead and throw in some vector signs here. So what that means for the net torque on the system to be 0, that means that the magnitude of the torque caused by this and the magnitude of the torque caused by that are going to have to be the same. So the torque caused by mg is just going to be, let's say 0, is equal to the torque caused by mg, which is 1/2 r. All right, our lever arm is actually half the length of the bar, times mg, because the force is the weight of the bar. That's actually what's exerting the torque here. It's the force of gravity on the bar. And this is exerting a negative torque. And remember, we only want the component of this force that's actually in the direction of that rotation. Right, so if this is theta here, this component is going to be f sine theta. And the lever arm is r in this case. Right, so the torque caused by this force is going to be r f sine theta. So we're able to write a statement right there using the fact that the net torque on the system is 0. Now let's go ahead and simplify, right? I can cancel out my r's. Let's move f sine theta over to one side. F sine theta is equal to 1/2 little mg. I'm just going to solve for f, because that's the thing that we don't know. And here we've got mg over 2 sine theta. That's going to be the magnitude of our force up there. So that's cool. Now let's go ahead and figure out what is going on with the hinge. Now this is a little bit harder, but there's a few ways we can do it. So that force that's acting on the hinge is going to have both an x and a y component. So this statement I made here about the fact that the net force on the rod has to be 0 also tells me that the total force in the x direction on the rod has to be 0, and the total force in the y direction on it has to be 0. And I keep misspeaking and saying bar or rod instead of bar, but right, we're talking about the bar, this heavy thing on top. So let's think about the x direction. Right, in the x direction, we don't have any force exerted by gravity, but there is one component of this force in the x direction, and that's going to have to be canceled out by this thing. Right, so this hinge is actually going to have a force sort of pulling it against the wall in order for the net force in the x direction to be 0. So the x component of this force would be whatever that is times the cosine of theta. So what that tells me is that the x component of the force from the hinge, I'm just going to go ahead and write that as hinge x component, it's going to have to be equal to F, right, this is F, times the cosine of theta. And I know what F is. It's mg over 2 sine theta. So hx is going to equal mg cosine theta over 2 sine theta, which is the same thing as mg over 2 tan theta, I believe. So there's the x component of this force from the hinge. Now let's think about how we could get the y component. Now, there's a couple ways we could do it. I think the best way to do it is actually to use torque instead of force. So if we think about it, we can actually change our axis of rotation. So our original axis of rotation, we had it as here. But I am going to actually try setting this point as our axis of rotation. Right, it doesn't matter. We can choose whatever we want because the object's not actually rotating. But if we choose this as our axis of rotation, well, now this force is not exerting a torque. This force is exerting a torque that way, right? Which means that the hinge has to be exerting a torque that way to keep this thing from rotating down, right? It has to balance out with the torque caused by mg. So I can say that the y component, hy, this is going to have to exert a torque to counter the torque caused by mg. The torque caused by the y component of this force from the hinge pushing up should be equal to hy times r. And this should be equal to the downward torque, or not downward, I guess out of the page word, right? The torque caused by this, which is 1/2 r, that's the lever arm, times mg. So the y component of that torque is going to be equal to 1/2 mg. So what that means is that the force from the hinge up here is going to have a component in the x direction this way and a component upward, and it's going to look something like this. Wow. That would be h. And its x component will be this, but to the left, and its y component will actually be up and equal to this. Right, so we actually sort of set up 3 different equations here. The first one, we called this our axis of rotation, and we looked at the torque caused by this force and saw that they had to add up to 0. That's what happened right here. So this came from looking at the net torque equals 0 and choosing this as our axis of rotation. This equation came from looking at the fact that the net force in the x direction had to be 0, right? So basically this component of this force had to be equal to this component of this force to keep this thing from moving. And then, oh no, that was this part. Yeah, that was this part. This was just the ending of this calculation. This part was saying that the x component here had to equal the x component here. And then this last part we got from talking about how the net torque has to equal 0, but we called this point right here our axis of rotation. So the torque down, right, the torque out of the board caused by this had to equal the torque into the board that way caused by this one. And we were able to solve for the magnitude of the force here. We were also able to solve for the different components of this force up here caused by the hinge actually on that bar.